So now we have a very interesting question which is based on okay. See, some of the standard textbooks classify this under the topic loss of motion. Some others put this under the topic rotational motion, uh, which actually, sorry, no, sorry, not rotational motion, under circular motion. Uh, but see, the reason why I have chosen this question to be in loss of motion is because this comes under the concept of friction, which is exclusively discussed in loss of motion and not circular motion. However, this includes both the topics from circular and circular motion and loss of motion. Okay, so before I go any further, I have a question for you. I written it over here. When a coin is placed on a rotating table, it stays and it slips. You will complete this equation. Okay, the relationship between F static and F centrifugal. Is it less than, or is it greater than, or is it greater than, or is it less than? Okay, so that's what you have to do. Okay, now if you know the answer, you can do that directly. Now, otherwise, what I would suggest is instead of going through this solution here, now those who want only the solution, you have it written over here, right? You can do the substitution and you have the answer then, direct answer then. But otherwise, I would request you to spend a couple of minutes more, or maybe more than that, to understand the concept of static friction, the limiting value of static friction, the angular velocity, relationship between angular velocity and angular acceleration, and all of this totally linked to the loss of motion here. Okay, so to make you understand that, what I've done is I've taken, uh, yeah, I've taken three diagrams here. Please give me a minute. Okay, so not three, we have four diagrams here. So what is this? What is this diagram depicting? See, we have a table at rest, and there is a coin placed on the table which is also at rest, which means I'll have to add it over here, table and coin as well at rest. Okay, now see, this comes under the classic problems in mechanics, which we call as the turntable problems, right? Turntable represents table which has a fixed base, a support, and then it rotates the disc on the support. Okay, so excuse me. So what we do is now we rotate this disk or rotate this table with some velocity. Okay, and what happens due to inertia, since this coin is placed on top of the disk, as the disk rotates, the coin will also rotate. Now, how many? Please don't be carried away these diagrams here. Please make sure that you focus on the diagram here. So, when this coin is rotating, what happens is this coin will acquire all the properties with respect to velocities as that of the table, right? Now we know that whenever an object is executing angular motion, there will be one component which is always perpendicular, which is always perpendicular to its motion, right? So that is the velocity component V here. All right. Now there is another component which we call it as a centripetal force, which will act always radially inwards. Centripetal force will always act radially inwards, right? So these are the two components which are present. These are two forces, or one velocity and one force which is acting upon the exactly the coin which is placed on the table. Now, for higher values of v, what will happen? For higher values of v, we know that the velocity vector, this vector would be larger, right? And the centripetal force, which is acting towards the center, will remain the same here, right? Okay. Now, for even higher values of v, what will happen is at some point the velocity vector would overcome this centripetal force, right? Or rather, the motion due to the linear velocity will overcome the angular velocity, right? I hope this much point is clear. Okay. Now let's try to understand the mathematical representation of whatever we have said so far. See, velocity of coin is equal to velocity of table, which is equal to 0. Am I correct here? Right? If this is correct, tell me what is the velocity of coin with respect to velocity of table? Exactly. It would be Vc minus Vd, which is actually equal to, let me use a different color here. Yeah, okay, which is actually equal to 0 minus 0, that is 0, right? Now in the second case, what is velocity of coin with respect to velocity of with respect to table? It is velocity of coin minus velocity of table, and since both of them have the same velocity, it will be omega 1, not the angular velocity. I'm just giving some random value here. So omega 1 minus omega 1, which is equal to 0. So the relative velocity in both these cases, what is it? It is equal to 0. Let us see in the third case. What happens in the third case? The third case, velocity of coin is equal to velocity of table is equal to some other value omega 2. We're talking about higher values of v. And what is the relative velocity here now? This actually will be equal to omega 2 minus omega 2. Therefore, velocity of coin with respect to table again remains 0 here. Right? Now let us see for very high values of v. What will happen for this very high values of v? We need to understand that at some point of time, okay, now uh, let us say at some point of time, this velocity would result in this velocity would result in the coin being displaced from the table, right? The coin will now be displaced from the table. Let us say the coin has reached this point. The coin has reached this point. The coin is no longer here. The coin is no longer here on the table. It has left the table, right? The coin is moving away with some velocity. Okay. Now the coin is moving, has left the table. It is moving with some other velocity, right? Let us call that as L3, velocity as L3. But the table will still now be rotating with velocity V3. And now if you see, velocity of coin with respect to table is actually equal to L3 minus omega 3, which is definitely not equal to 0, right? What are we talking about? Relative velocity of coin with respect to table. So in the first case it was 0, second case for 0, so smaller values of v 0, higher values of v, relative velocity is 0. For even higher values of v, at one point when the coin bounces off the table, the relative velocity is not equal to 0, right? Okay, and it is at this point that we say that the coin has slipped. It is not the essential or the literal meaning of slipping. No, slipping means, see, this is one of the primary concepts where students always make a minute not detailed understanding of the words given in the question. Slipping means that there is some relative velocity, which when I say some, it is not equal to 0. Relative velocity between the coin and that of the table. I took a long time to explain this, but I wanted you to visualize the concept here, because see, if you don't visualize things, you won't be able to make your concepts clear. All right. So what does it mean when the coin has slipped? It means that there is some relative motion between, there is some relative velocity between the coin and the table. All right. So that was about slipping. Now let us slowly bring in the concept of friction. Let's see what happens in the case of friction. Okay, maybe I should keep this part. Oops. Excuse me for a minute. Yeah. So now let us try to understand what happens with friction here. See, when the table and the coin, both of them being at rest, there is no concept of static friction, right? Because static friction is at rest. But when there is an external force applied and when the table is rotating, static friction will come into picture. For low values of v, the static friction, we know that the value would be less than or equal to mu s into n, right? Now, as the values of velocity becomes higher, what will happen? Static friction value will be more than the static friction value in the first case. So SF2 will be greater than SF1. But even in both these cases, the static friction value will be either less than or equal to the mu s into n, right? But as soon as the value of static friction is greater than mu s into n, what will happen? Exactly. What happens is the relative velocity between these two bodies will come into picture, and as a result of which there will be slippage of coin. Okay, so what I've done is I have showed you what slipping of coin is. Then we discussed in detail the relationship between slipping of coin and that of coefficient of friction and, for that matter, static friction. Okay, right. Now, what I want to do is I want you to visualize this concept here. I'm not going to derive things in detail here. Because it's okay now. I think it's almost close to 10 minutes, which is more than the normal value, normal than time we use for discussing problems. However, these kind of concepts, these kind of questions enrich your understanding about the question, the concepts, and that's why I'm trying to try to give more emphasis on the problem here. Okay, so what I've done is earlier we were discussing one circular disc and one coin on it, right? In this case, I have taken one circular disc and two coins. One coin which is at a distance r1, the other coin which is at a distance r2. From where? From the center of the table. All right. So we have r1 and r2. So first step of the solving the problem, which is, okay, maybe I should keep that flowchart as a reference because some of you will repeatedly be asking about the same thing. Maybe I'll do that now. Okay, so this is the flowchart here. We need to first visualize it. Frame of reference. As usual, I'll stick on to the inertial frame of reference, which means the observer is standing out from the from wherever this picture is happening. Then a system. We have the system, which is the disk and the coin. Isolate the body. Isolate the body. Isolate the body. The body is isolated here. Then sigma of x, sigma of y. We have drawn n1 mg, n1 m1g, n2 m2g. Now, what is sigma fx? Sigma fx will be equal to m into an. What will be sigma fx? Here it will be m into n. Same in the both cases because both of them are on the same table. What will be sigma fy? Since there is no vertical motion, I repeat, since there is no, which means the coin is not lifting, it is not getting lifted into the air, it is not thrown away into the air vertically. It stays, whatever motion it follows only along the horizontal motion. And there will be one force acting like this, which will be the friction force. There will be one force acting like this, which will be the force of friction, right? And then I think the rest is already been explained in the first part. As velocity increases, value of frictional force increases, velocity increases, value of frictional force even increases. But at some point, when the velocity increases beyond the force of static friction, the coin slips. Okay. Now what you can do is you can do the both of the comparisons and tell me what will be the relationship between these forces when say when okay wait I think it's better that if you make a note of this, I can complete this, and we will discuss this in detail when we see the given question. Yeah, that would be better because that comprises of even the discussion in even better detail. Give me a second, let me just minimize this thing, right? And we will, yeah, okay. So now coming back to our question here. All right. So according to the question, we've been given two different conditions, right? We've been given two conditions. What is condition number one? Condition number one is that it is placed at a distance of 1 centimeter. What is condition number two? Okay, sorry. Both of them are placed at a distance of 1 centimeter. Is it? Distance of 1 centimeter from the center. The angular velocity will be the distance of from center. Yeah. So the second condition, R2 is not equal to R1. There is some displacement from R1. Okay. Right. Now, what we'll do is we'll try to understand the various forces acting on it. See, again, the flow chart, as you asked, is really important here. We visualize the concept with the question, and now we'll introduce the free body diagram. Now, what's the free body diagram of first case? So we have a coin here, table here. The coin is rotating like this, which means definitely there will be F centripetal acting along the x direction, right? And what does it mean when sigma Fy is equal to 0? sigma Fy is equal to 0 implies that n will be equal to mg, right? Now, what I want to do is the previous discussion when we wrote R1, R2, and coin 1, coin 2, I wanted to extrapolate the same discussion, same derivation over that. Okay. Now, I'm not going to do that because that's not a point of discussion here. Okay. Now, what is sigma fx? Sigma fx is equal to m into a m into a. Let's say m into a. What a is here? Is it linear acceleration? No. Why? Because the circular motion, that would be a centripetal, right? What is a centripetal? A centripetal is v square by r. So what is sigma fx is equal to m into v square by r. Now, what is sigma fx? All the forces acting along the sum of all the forces acting along the x direction. So there is only one force which is acting along the x direction, which is the f centripetal, right? So we have f centripetal is equal to mv square by r. Come on, this is something very basic to circular motion. But why are we discussing that in laws of motion? Because this circular motion over here is taking place due to the centripetal force, which is actually a name that we give to a pre-existing force, which is nothing but the force of friction. So what is the centripetal force here? Centripetal force here is nothing but the force of friction. I repeat, what is centripetal force? Centripetal force is nothing but the force of friction. So we can replace F centripetal with the force of friction. And which friction is acting here? Now things become really conceptual here. It is not the kinetic friction. It is rather the static friction, right? Because the coin is still at rest. And now we have F static replacing F centripetal. So what is F static? F static is equal to mu s into n. And what is n? N is equal to mg. So we have mu s into n is equal to m into v square. What is v square? R. What is v? V is r omega. What is v square? R omega the whole square. So what we get is mu s into n is equal to m into r omega square. And if you do the same thing for the second, for the same coin, capital distance r2, what you get is mu s into n is equal to m into r into omega square. Okay. Yeah, now you may be wondering what is the difference between these two. The difference between these two is that the angular velocities is different. So this is actually omega 1 square and this is omega 2 square. However, what remains same is the value of mu s into n. Why? Because in both the cases, mg is same because it is the same coin which is kept at two different positions. Therefore, mu s into n and mu s into n would be same here, which means mr omega 1 square will be equal to mr omega 2 square. And if we see, m and m will be same, r and r will not be same. It will be r1 and r2, right? So we have r1 into omega 1 square is equal to r2 into omega 2 square, but it is given that the angular if the angular velocity is halved, so we can say that omega 2 is actually omega 1 by 2. Therefore we can say that r1 into omega 1 square is equal to r. Instead of omega 2, what can I write? Omega 2, I can write omega 1 by 2 the whole square. Therefore r1 into omega 1 square is equal to r2 into omega 1 by 2 the whole square. And therefore this becomes r1 is equal to r1 is equal to r2 into, so this is omega 1 square into omega 1 square by 4. Omega 1 square by omega 1 square is 1, and therefore what we get is r2 is equal to 4 times r1. And what's the value of r1? It is 1 centimeter. So this becomes 4 into 1, and therefore the value of r2 is 4 centimeter. So r2 is 4 centimeters. It's a lengthy explanation, I do understand, but the reason why I made it so lengthy is to make sure that you understand, number one, what is slipping of coin. Number two, relationship between slipping and the friction. Then static friction, kinetic friction, and then understand relationship between centripetal force and friction here. All right. Okay. So yeah.